So we've talked a lot about the normal distribution and the standard normal distribution. And so we're going to focus on one sort of more aspect that has to do with this idea of normally distributed. And it's going to have to do with our central limit theorem for sample means. So the first thing that we're going to look at and sort of define is a statistical inference. So statistical inference. It's to make accurate decisions about population parameters from sample statistics, right? So we're going to take a sample and then try to compare it to what maybe what's happening in the population. We can also look at the sampling distribution. And this is how a sample statistic is distributed when repeated trials of size n are taken. So some questions that could arise, is the sample mean a variable? In other words, is it a fixed quantity or does it vary, right? If you're taking these random samples, is it fixed or does it vary? So let's think about, like, if we consider the students in our class as a population of interest. If we wanted to estimate the average age of students in our class using a sample of size 4, does that quantity, the mean age for a sample of size 4, vary? Probably, right? Depending on who you choose. What about suppose our population of interest is 5 dogs? So Max, Drake, Kudo, Rusty, and Lex. Then our population size is n is equal to 5. Our variable of interest is the leaping distance in feet each dog leaps off of a deck. Each dog's leaping distance is as follows, right? So we have Max, Drake, Kudo, Rusty, and Lex. So let's just, you can pause it, but go ahead and find the mean of these, right? Add them all up, divide by 5, and see what you get, right? So if you do this, you should get a mean, right, of 17.7, right? That's the mean of all of the dogs. That's the mean of our population. So the sample mean, right, leaping distance, x bar, is a variable which takes on a different value. So consider several different cases shown below. So our first case is the sampling distribution of the sample mean for samples of size 2. So let's say I take, right, and you can sort of see all the possibilities here, 2 of the dogs, right, and find their sample mean. So if I think, right, the first one, Max and Drake, 15.2 and 19.5, I add those, divide by 2, I get a mean of 17.35, right, a sample mean. And if I do this for all of these, right, you'll notice that they do vary, right? Some of them are higher, some of them are lower than our 17.7. So what I want you to do, and you can do this, you can trust that it is, but if you were to add all of these up, right? So if you were to take the sum of all the sample means, divide it by 10, what would you get, right? We would get a mean of the sample mean is 17.7, which, if you remember, that was the mean of the population, right? So that's for a sample size of 2. So let's think same thing for a sample size of 3, right? So now I'm taking 3 of the dogs, finding the means of those 3 leaping distances, and then at the very end, right, I'm going to take and add up all of these here, right? So add up all of the sample means, x bar, I can divide it by 10, and I find, right, that its mean is 17.7. So I can do this again, the same thing with a sample size of 4. So again, right, if I take the sample mean for samples of the size, and then, right, I have 1, 2, 3, 4, 5 in this case, so I take this, add up all the sample means and divide it by 1, 2, 3, 4, 5, I get, right, 17.7. So the idea, again, is what we're going to show, and what we're trying to say is that this mean of the sample means, the 17.7, we call this an unbiased estimator. Because although each of the sample means differ, right? If we add them all up, we end up with the same population mean. So it says, notice that for each of the above sample sizes, the mean of all possible sample means was equal to 17.7, which was the population mean leaping distance for the 5 dogs. That shows us that the mean of all possible sample means is equal to the original population mean. So symbolically, we say, and I'll write it a little bigger, that the mean of the sample mean, so mu of x bar, is equal to the population mean. All right, so that's how we would write that. So I want you to sort of consider this. Now let's consider the spread or the standard deviation of all possible sample means. It is easiest to see using a graph of the possible sample means for each possible sample size, right? So let's take a look at what we see here, right? So we see, here's my population mean. Here are my original, right, observations. And so each of these little stars are the possible sample means, right? So if I take two of these, maybe it's this one here and so forth. So all the different possibilities. And you'll notice, right, that n is equal to 2, the spread is really quite large. N is 3, it's a little bit smaller. When n is 4, right, it's even smaller. And then when it is 5, right, it's the same. So we would say that as, right, the sample size increases, the spread of possible means decreases. And so we notice, right, the pyramid shape above, the spread or the standard deviation is the greatest when looking at all 5 individual observations. This spread is represented by the notation, so it's sigma of x bar. So once we consider all possible sample means for a given sample size, the spread begins to decrease. In fact, the larger the sample size, or n, the smaller the spread or the standard deviation of the possible sample means. The spread of all possible sample means for a given sample size is represented again by the notation sigma of x bar and is dependent on both the population standard deviation and the sample size. Specifically, right, and I'll write it a little bit bigger so you can see, right, so we sometimes call this the standard error is equal to the population standard deviation divided by the sample size, okay? So as more of the observations from the population are included in the sample mean, or x bar, should become, on average, a better and better estimate of the true population mean mu. Thus, the possible values of the sample mean become more tightly clustered about the true population mean. So far we've just sort of talked about if we have a population, sort of how it differs if we're taking, the sample, finding the sample mean, and then looking at the standard error as well. So in the next video, we'll talk about what this all means with our central limit theorem.